All right, hello everyone. Welcome to my channel. This is a channel that is dedicated toward educational matters, particularly shedding light on little known authors, little known theories of everything, cosmologies, all encompassing theories that the author or authors spent lifetimes, or at least one lifetime, working on, but never really got the traction out in the kind of the public to get their theories out there. Today is video number 183 on the reciprocal system of theory. And this is a theory that was originally devised by Dewey B. Larson way back in about 1930, and he kept working on it, kept plugging away. First, a long period of inductive reasoning to take the specific to the general, and then he arrived at his fundamental postulates and two postulates, and then he took those two postulates and he took that through a process of deduction, going from the specific to the general, general to the specific, and basically a process of if this, then that, and he derived an entire theoretical universe from his postulates. I went over that in about 15 videos earlier here. It's called a talk that he gave called The Outline of the Deductive Development of the Reciprocal System. And, he starts with the postulates and then goes, if this, then that, if this, then that. And his theoretical universe is very similar to the actual universe that the legacy scientists have discovered through their observations and their measurements. So the basic idea in the postulates in Larson's system is that we live in a universe of motion. The universe is made out of motion. It's not made out of matter. It's not made out of energy. In particular, matter and energy are actually just two different kinds of motion. And motion in general is the relationship between space and time. So that sets up a generalized reciprocal relationship between space and time, hence the name reciprocal system. Motion is basically a fraction with time or space as the numerator and space or time as the denominator. And all of our basic scientific quantities are actually just kinds of motion, because you have both time and space are multidimensional. That's what Larson calls a coordinate space and coordinate time, three or more dimensions of both space and time. And they have their scalar aspects, which Larson calls clock time and clock space. That's scalar motion is a motion that has a magnitude but has no particular direction. The clock is always getting later and later and later. And in terms of space, the clock is always getting farther and farther and farther apart. So space is always getting farther and farther apart, but in no particular direction. Space and time also have their discrete units, so there is a minimum unit of space and time. There is no such thing as space or time under less than 1 unit. And ultimately, there's no such thing as space or time at all. They only exist in the context of motion. They only exist together in motion. And when you have exactly 1 unit of space in 1 unit of time, you have the speed of light. That sets up the speed of light as being really the midpoint of the universe, the 0 point, the origin or the ether of this universe. Larson calls it the progression of the natural reference system. That is a motion outward at the speed of light in all directions. And from that, he basically derives his whole universe. We're looking at his 1979 book called Nothing But Motion. Here he's basically using these same principles to derive atomic physics and then some organic chemistry later on once he sets it up. We just got done with the chapter 11 on the subatomic particles. Chapter 10 was on atoms. And now we're about to start chapter 12, which is called Basic Mathematical Relations. Okay, let's hear from Mr. Larson. It was pointed out in the introductory chapters that when we postulate a universe composed entirely of motion, every entity or phenomenon that exists in this universe is either a motion, a combination of motions, or a relation between motions. The discussion thus far has been addressed mainly to an examination of the primary features of the possible motions and certain of the combinations of these motions. At this point, it will be advisable to consider some of the basic kinds of relations that exist between motions. Inasmuch as motion in general is defined as a relation between space and time, expressed symbolically by S/T, all of the different kinds of motions and the relations between motions can be expressed in space-time terms. Such an analysis into space and time components will be particularly helpful in putting the various physical relationships into the proper perspective. And our first objective in the field we are now entering will therefore be to establish the space-time equivalence of the various quantities that constitute the so-called mechanical system. Consideration of the analogous quantities of the electrical system will be deferred until we are ready to begin an examination of electrical phenomena. One set of these mechanical quantities is customarily expressed in velocity terms, and it presents no problems. One-dimensional velocity is, by definition, S/T. Now, just to clarify a little bit, S/T is speed and or velocity. Speed is the scalar form of velocity. So speed is 10 miles per hour. That's space over time. What velocity adds is it adds a vector, it adds a direction. So velocity is space over time, but it's in a specific direction. Space over time, 10 miles per hour due north would be velocity. It follows that two-dimensional and three-dimensional velocity is s squared over t squared and s to the third power over t to the third power, respectively. Acceleration, the time rate of change of one-dimensional velocity, is s/t squared. I dropped the ball and it fell at 9.8 meters per second squared. That is acceleration. In addition to these quantities which express motion at velocities or speeds, there is also a set of quantities which are fundamentally based on resistance to movement, although in some applications this basic significance is obscured by other factors. The objects which resist movement are atoms and particles of matter, three-dimensional combinations of motions. In a universe of motion where nothing exists but motion, the only thing that can resist change of motion is motion. The particular motion that resists any change in the motion of an atom is the inherent motion of the atom itself, the motion that makes it an atom. Furthermore, only a three-dimensional motion, or motion that is automatically distributed over three dimensions, is able to offer effective resistance, as any vacant dimension permits motion to take place without hindrance. The magnitude of the resistance can be expressed in terms of the quantity required to eliminate the effective existing motion, that is, to reduce this motion to unity in the conventional reference system. This is the inverse of the motion of the atom, s to the third power over t to the third power. And the resistance to motion, or inertia, is therefore t to the third power over s to the third power. In more general application, inertia is known as mass. Inasmuch as current physical theory recognizes gravitation and inertia as phenomena of a quite different character, the equivalence of gravitational and inertial mass, which has been experimentally demonstrated to the almost incredible accuracy of less than 1 part in 100 billion, is regarded as very significant, although there is considerable difference of opinion as to what that significance actually is. As expressed by Clifford M. Will, quote, the theoretical interpretation of the Eötvös experiment, which demonstrates the equivalence, has varied. Will asserts that it is now believed that the results of this experiment rule out all non-metric theories of gravitation. He defines metric theories as those in which gravitation can be treated as being synonymous with the curvature of space and time. After the theorists have arrived at such a far-reaching conclusion on the basis of what Will admits is no more than a conjecture, it comes as something of an anticlimax when the reciprocal system reveals that nothing of an esoteric nature is involved. Gravitation is a motion, but it can manifest itself either directly as motion or inversely as resistance to another motion. Multiplying mass, t to the third power over s to the third power, by velocity, s over t, we obtain momentum, t to the second power over s to the second power, the reciprocal of two-dimensional velocity. Another multiplication by velocity, s over t, gives us energy, t over s. Energy, then, is the reciprocal of velocity. When one-dimensional motion is not restrained by opposing motion, it manifests itself as velocity. When it is so restrained, it manifests itself as potential energy. Kinetic energy is merely energy in transit, so to speak. It is a measure of the energy that has been used to produce the velocity of a mass. This is 1/2 mv squared equals 1 over 2t to the third power over s to the third power, which is matter, times s to the second power over t to the second power, equals 1/2 t over s, and can be extracted for other use by terminating the motion. This explanation of the nature of energy should be of some assistance to those who are still having some difficulty with the concept of scalar motion. Both speed and energy are scalar measures of motion. But on our side of the unit speed boundary, the low speed side, where all motion is in space, speed can be represented in our conventional spatial system of reference because it causes a change of position, inward or outward in space, whereas energy cannot be so represented. On the high speed side of the boundary, that is the cosmic sector, in the relations are inverted. There are there all motion is in time, and the measure of that motion, the energy, t over s, the inverse of speed, s over t, can be represented in a stationary temporal reference system, whereas speed is neither inward nor outward from the time standpoint and cannot be represented in the temporal coordinate system. Here is the reason for the purely scalar nature of any increment of speed beyond the unit level, such as those discussed in Chapter 8. The added speed does have a direction, but it is a direction in time, and it has no vectorial effect in a spatial system of reference. We will find this very significant when we undertake an examination of some of the recently discovered high-speed astronomical objects in Volume 2. Force, which is defined as the product of mass and acceleration, F equals ma, becomes t to the third power over s to the third power times s over t to the square, t squared equals t over s squared. Acceleration and force are thus inverse quantities in the sense in which that term is generally used in this work. That is, they are identical except that space and time are interchanged. They are not inverse in the mathematical sense, as their product is not equal to unity. One special type of force that is of particular interest is the gravitational force, that which the aggregates of matter appear to exert on each other by reason of their motions inward in space. In this case, the mathematical expression F equals constant m1 over distance squared, by which the force is ordinarily calculated, is quite different from the general force equation F equals ma. When taken at their face value, these two expressions are clearly irreconcilable. If gravitational force is actually a force, even a force of the as-if variety, it cannot be proportional to the product of two masses, that is to m squared. When force in general is proportional to the first power of the mass, there is an obvious contradiction here. Most of the other common quantities of the mechanical system can be reduced to space-time terms without any complications. For example, impulse, the product of force and time, has the same dimensions as momentum. F times ft equals t over s squared times t equals t squared over s squared. I'm not too sure about that one. I was under the impression that impulse was t squared over s. Anyway, both work and torque are the products of force and distance and have the same dimensions as energy. Work and torque, Fs equals t over s squared times s equals t over s. Pressure is force per unit area, which is T over S. I'm not sure where he's getting this from exactly, but pressure is force per unit area. That's T over S squared divided by S squared. So pressure is T over S to the fourth power. Density is mass per unit volume, and that is mass is T to the third power over S to the third power times 1 over S to the third power. And so that is T to the third power over S to the sixth power. Viscosity is mass per unit length per unit time. That works out to be T to the second power over S to the fourth power. Surface tension is force per unit length. And that turns out to be T over S to the third power. And then power is work per unit time. Power is 1 over S. That's energy per time. T over S times 1 over T equals 1 over S. All of the established relations in the field of mechanics have the same dimensional consistency on the basis of these space-time dimensions as in the conventional forms, since the mass terms in the equation are in all cases balanced by derivatives of mass on the opposite side of the equation. The numerical values in these equations likewise retain the same relationships, as all that we have done from this standpoint is to change the size of the unit in which the quantity of mass is expressed. What has been accomplished, then, is to express mass in terms of the components of motion. Since mechanics deals only with space, time, and mass, it follows that, so far as mechanics is concerned, by reducing mass to motion, we have confirmed the validity of the basic postulate that the physical universe is composed entirely of motion. Okay, we will leave it there, and we will probably go over this paragraph again and then proceed onward in this chapter on basic mathematical relations. Thanks for tuning in. Have a great day.